Hello again, guys, and welcome to this series, which is on machine learning fundamentals. We were discussing, in fact, about reinforcement learning. The previous, this same episode, but the previous part of it. We were discussing about the reinforcement learning and the related concepts that are there. And in fact, we had reached to one point where we just listed down different reinforcement machine learning algorithms that are there. In fact, there are numerous, and out of those, we are going to discuss some of them. And then definitely a little bit about the Q learning, which is the core algorithm as far as the reinforcement algorithms are reinforcement machine learning is concerned. So I'll be starting from the same point where I left. So little bit of, in fact, info about the Q learning. Maybe a couple of slides I might have to take back, and I'll be just brushing them up very fast, and then after that, I'll be taking the content that is intended for this particular part of the episode. So let me just put to my presentation. uh, this is exactly the same point we had seen this mathematical expression which is there, and the terms that are given. If you just see current value, R is the reward, and then S is the next state, and then we are having alpha with the learning rate, and then there is in fact gamma, which is the discount factor. So simple interpretation, update knowledge based on reward and future potential. But I would like to first of all emphasize on few of the things. In fact, learning rate and next state reward we have already discussed. Learning rate is also upcoming. But what is this discount factor first of all? So a little bit of elaboration on this so that you can understand it better later on when we are putting it. So meaning of discount factor, which is gamma. The discount factor determines how important are future rewards. So it ranges between 0, which is less than or equal to gamma is less than or equal to 1. So we can just see that it ranges from 0 to 1. So the value of gamma will range from 0 to 1. And there is definitely an interpretation which is given, and from there we'll understand it better. So we can take two cases here. Case one is if the value of gamma is equivalent to 0, the agent only cares about immediate reward. If this thing happens where the value of gamma is equivalent to 0, or it is close to 0, so what agent will do, it will care about the immediate reward. So it will not be caring about the future reward, so it will not be futuristic, so it ignores the future rewards. Example is if current action gives you +5 now, future reward of +100 later is ignored. So definitely it will not be the when the gamma value will be near to 0 or 0, it will not be caring about the future uh, you know uh, future gain which is there, or the future award it is there. There's a reason for that. Why this behavior is in fact short-sighted, greedy, fast but not strategic. So that is there, but there's a reason also for this. Why this happens, because when the gamma value is coming near to 0, so there is a less possibility, or you can just say you need to make multiple steps before you can just gain something in the future. So that gets actually overshadowed by the immediate gain that we are having, so even if it is lesser. So that's why in fact this is called as a discount factor. So you are having discount, you are having this time itself you are gaining it. So that's the reason this is called as a discount factor as well. So because when the value of gamma is near 0 or it's equivalent to 0, there is after making multiple steps, there's a possibility that you might be having a gain which is bigger. That is one case. Second case is when the gamma is close to 1. So for example, it is 0.9 or 0.99. The agent strongly values future reward. Why it is doing this? Agent may sacrifice the small immediate reward to gain the larger future reward. And why it happens like that? The behavior is strategic, long-term planning, better for complex tasks. But there is a probability, actually the possibility is that in near within one step or so, or two steps, next two steps, it is going to have a major gain coming up. So that's why it is taking a different approach, which is futuristic. So these two cases are there. In fact, Q learning, what is Q learning? First of all, we had discussed a little bit in the previous part of this episode. Q learning is a reinforcement learning algorithm where an agent learns the best action to take in each situation by interacting with the environment. So it is agent which is learning that what is the next best action that can be taken based on the current situation. It learns through various things. For example, trail and action is there, reward and improvement. The agent does not need a teacher telling it correct answer. It is actually learning by rewards and penalties that we discussed in fact in the previous part in quite a detail. So Q learning is a value-based reinforcement learning algorithm that learns the quality, value of actions in different states so that the agent can choose the best action to maximize long-term reward. So that is there. It's a value-based reinforcement learning algorithm. It learns through quality value of actions that are taken, and it is the overall motto of this is that it should be maximizing the long term reward. The word Q means quality of an action in a given state. So this is what, in a very simple definition, I think we had in fact done it the law previous time itself, the first part of this particular series. You can just take an example, real life example is that we can imagine a student trying to find best route from classroom to library. The student can move up, he can move down, left, right. So some paths are short, some are blocked, some paths waste time. After trying many times, student learns. So from this position, the direction is the best. So this is Q learning. So when the student realizes after making moves, after going maybe wrong several times and doing certain right steps as well, many right steps as well, then what happens is it is taking a learning of this, that how to move from this position to in which direction it has to be moved, and then it reaches to its destination. This is Q learning. So we are going to exactly see that as the and the implementation as well. We'll just see in Python. So core terms that are there in Q learning: agent is there, the learner or the decision maker. We had discussed it earlier as well. For example, a game player, a robot, a game player, a student navigator, anybody. This is an agent. And the environment is there. Environment can be a maze where you are moving something. It can be a game in which a player is playing. It can be a classroom map, game board, road system. It can be anything. So which is an environment. So different environments can be there. And the agent, the learner or the decision maker, robot, game player, student, navigator, environment is the world in which the agent acts. So this can be maze, classroom map, game board. So any environment can be there. And there are definitely core terms that we had to just go through. State is the current state in which the agent is there. The current cell in the grid can be the current state. The action is that you have to make a possible move, and you have to make a move that can that agent can take the next. So it can go up, it can go down, it can go left, it can go right, depending upon the environment. Actually, these are just the examples which are given here. It depends upon the environment what you're having and what actions you can take, but these are just some of the examples that are given so that you can understand. So feedback from the environment example is +10 for reaching the goal. It will be -1 for each step, and -5 if you are hitting a obstacle. So if you're having an obstacle, you are hitting that, and that means the wrong move is made, then you'll be having -5. So this is the reward and penalty thing which is given, and this is a Q table where you are having these table that stores the value of each action in state. So value of each action, that means if you're moving up, what reward you're going to get, what is the value of that. If you're going down, what is the value of that, left, right, all of those things are there. So from state S1 and then state S2 it is showing if we are making these moves. So that's called as a Q table. And there is definitely this formula which we had taken in fact earlier as well, which is consists of learning rate, which is alpha. How quickly your this agent is learning. Current Q value for state and action. Reward is received, so R. Gamma is the discount factor which we explained in fact just now. Next state is the S. Then you are having best future Q value from next state. So these are some of the parameters that you have to understand a little bit to see this. So the formula says update the current action value using the reward received and the best possible future reward. So this is what the formula is. Actually, if you are interpreting this formula, this is what it is. So you are updating the current action value by using the reward received and the best possible reward. And the learning rate, which is alpha, controls how much new information updates old information that is with you. High alpha means learns quickly. Low alpha means it learns, the agent is learning slowly. So discount factor, as we have already discussed it in quite a detail, it cares only about immediate reward. If the gamma is near to 1, cares strongly about the future. So it controls how the agent cares about the future rewards. And then epsilon, which is there, controls exploration. High epsilon agent, I think this we had discussed in the previous part of itself. Agent tries random action. If it's low epsilon, agent uses the learn best action. That means if the epsilon e is low, that means you are already having learning, which is which through which you can take the best action based on the previous experience you are having. So exploration, trying new actions to discover better paths. Examples, a student tries a new corridor. So this is exploration. And then there is exploitation. If you already know some, this way or a path, so you will not be exploring something new. You will be going through that path which you already know. The student uses the shortest known route, which is known to him or her. So a student is using that. So using the best known action. uh, why the balance is important? Balance between the two is very important because we need to just see that it cannot be stagnated. A model is there, if even if you're having a path which is already there, and then you are having a shortest path, but it is a continuous learning process where improvements can happen. So it has to be a balanced kind of a thing, that it should not be that it's always going with the previous this one. So it should be learning, new knowledge also should be gained. If the agent only explores, it never uses what it learned. So that is one factor of it. If you're not utilizing what you have learned. And if it is only exploiting, it may miss a better solution, which can be there. So you might have searched for one solution which is good, but you might be getting an excellent solution as well if you're exploiting. So this example scenario, grid world, we can create a simple 4 into 4 grid. So this is the grid which is showing from here. The 4 into 4 grid, you can just see 4 from here, four columns, 4 rows. So this is a start, and this is in fact the goal, where from we have to start, and the goal, what will be the best possible route which one can take and navigate from start to goal. So if we can just see this, where S is start, G is goal, the agent can move up, down, left, right. Rewards are reaching goal 10, -1 is every move, and the goal learns the best path from the start to the goal. So it learns the best path. You can just see environment setup, grid size is 4, creates a 4 into 4 grid. Num states, grid size into grid size. So 4 into 4, 16 states are there total. So those are the states, numerical states which are there. So there are 16 states. Start and goal, start state is equal to 0. The goal state is 15. State 0 is equal to top left, and state 15 is equal to bottom right. So these are all the facts which are there for the grid. You can just see those. Actions you can take up, down, left, right. The agent can move in 4 directions. Q table is equivalent to np dot zeros, num states, num actions. So creates a table with 16 rows equals states, 4 columns is equal to actions. Initially all values are 0 because the agent has not learned anything. So you are having everything with the 0. There's no value associated with any of the positions because agent has not learned anything. Hyperparameter, learning rate is equal to 0.1, discount factor is equal to 0.9, epsilon is equal to 0.3, episodes 1000. Meaning learning rate, how fast an agent is learning. Discount factor, importance of future reward. Epsilon is probability of random exploration, and episodes, number of training attempts. That's why we said that epsilon, probability of a random exploration. If it is low, then it will not be taking. If it is high, then it will be going for the future, this one, exploitation. So moment function. So it takes action state. This function moves the agent based on selected action. So we just moving the, if the agent reaches goal, reward is equal to 10. So then otherwise reward is equal to -1 if it is, just one step, it is not reaching the goal, so one step is done. So definitely, so this is exploration versus exploitation. This means sometimes agent explores randomly, otherwise it chooses the best known action, that we already know. So q value update, this is the core learning step. It updates the q value using the current state, reward, future expected reward. So all of this is there. And in fact, I'm having one program on this. Basically, this is actually the grid we have seen. We just see this grid, exactly this grid will be implementing. So in fact, we are seeing the output of this. So this grid, I have done it in the Python. You can just see this. There's a program. So import numpy. It's very simple. Importing the random, and we are using these. Grid size is equal to 4 states. Start state is equal to this, and action up, down, left, right. We are just giving this initialization of num states or grid size into grid size. So that is 4 into 4. So these are the states which we will be getting 16 states. Table is equal to NP is also exactly the same thing what we did have seen in the PowerPoint. Same thing we are doing here. So Q table initialization happens here. So this Q table initializing. And then we are putting hyperparameters. Learning rate is equal to 0.1. Count factor is equal to 0.9. And epsilon is equal to 0.3. Episodes 1000. Max steps 50. And then state position, row is equal to state. Okay, definition of, we are defining this. We're defining state to position and position to state. So these two things, and then take action, that also is there. One more, prevent moving outside grid, so that prevention is also there, so that it does not go beyond the grid which is there. 16 by 16 states. And then it is just returning, and it putting for episode, this one for loop is there. So you can just see very simple code, which is, but nothing much as far as the machine learning is concerned. So it will be just giving you the path actually with this star. If you just see this code properly, it will be giving us the path where from it is moving from the start to the goal. So that path it will be showing us. It will be printing that path, in fact, with the program. So that path has been printed here. If you can see. So this is actually the simple Python program. It is not having anything much as far as technicality is concerned, or the complexity of the program. So you just see this is the grid path where start is made, and then it is going one step right, and then again right, and it's going down one, two, and then it's moving again right, then it's three. So this is one path. It can have multiple. It can go directly down and like this. That also can be there. So there are multiple paths, but it is calculating this time that this is the path which will be going. And in fact, it is showing that path from start to, and then these are the 16 states which it is showing. In fact, every state is having one associated number, showing that how worth this step is going to be. And then it is saying that learned path is 0, 1, 2, 10, 11, 15. I think as in when you are changing it, you're again executing the program, it will not be taking the same, taken some. So if you third time, it might be taking some. If you execute it again, different path. Here also it has taken a different, going like this down and then like this. So there can be, it can learn, in fact, best path which is there, and learned paths which is one more path which has. So it may be able to take the best, but it is continuously trying to learn. So that's why we find that because that aspect of exploitation has to be there. It should not be that one path is learned then it will be going again the same thing. Maybe you're able to find something better. So I think that's it. We are done with this one thing, which was this, algorithm which we have taken, first one, that is fact, Q learning formula or Q learning. So, core terms in Q. All of this we have discussed about Q learning as well with example. So we shall be in fact back with one more part of this particular important machine learning falling in this category of learning. So much once again for joining and provide us your valuable feedback so that at future recordings and lessons which are there. And thank you